Professor VVSH Prasad, Department of Mechanical Engineering, Institute of Aeronautical Engineering, in the development of the video content in the subject of kinematics of machinery. Today we are going to deal with the Grubler's criteria in the kinematics of machines. The relation between the links, pairs and joints is given by two scientists and two mechanical engineers or two theoreticians, one by Cudbach equation, other one is Grubler's criteria. The most popular one is Grubler's criteria. Before going to Grubler's criteria, we will look towards the Cudbach equation also, where L is equal to 2p minus 4 and J is equal to 3 by 2 into L minus 2, where L is equal to number of links, P is equal to number of pairs and J is equal to number of joints. In the equation where we look into that, when LHS is greater than RHS, then the linkages where we have joined, they will be called as the locked chain. When LHS is equal to RHS, the linkages of assembly we call it as the constrained kinematic chain. When LHS is less than RHS, it is called as unconstrained kinematic chain. When we look at it, the locked chain or structure, links connected in such a way that no relative motion is possible. And in that, J is equal to 3 by 2 into L minus 2, where L is equal to 3, J is equal to 3, P is equal to 3. And if you substitute back in the equation, J is equal to 3 is equal to 3 by 2 into 3, which is going to give as 4.5 minus 2.5. Therefore, when we look at it after substitution, LHS is greater than RHS. Hence, if we apply this criteria to a binary joints containing the turning pairs, then link 1, 2, 3, in which if we consider number of binary or turning pairs are 1 to 2, 2 to 3 and 1 to 3. There are 3 joints and 3 links, and when you apply in your equation, J is equal to 3 by 2 minus L by 2, and here if we apply that equation, J is equal to 3 by 2 into 3 minus 2. Then in that case, this goes 1.5 times and this 3 into 4.5 minus 2, and where is, therefore LHS is 3, which is greater than 2.5. Hence, we consider this as the a locked chain. We consider this as the locked chain. Then when you go for the next one, a kinematic chain, slider crank or 4-bar mechanisms, in which if you look at it, the link 1 is fixed and A0 and B0 are the fixed points. Link 2 rotates in clockwise, link 4 rotates in clockwise direction, and link 3 is a coupler link connecting the link 2 and 4. In this also, if we apply our criteria, where in the equation where we have applied J is equal to 3 by 2 minus L minus 2. J is equal to 3 by 2 minus into L minus 2. In this case, where J is equal to, there are 4 turning pairs and 3 by 2 into 4 minus 2. Therefore, it goes as 2, which is equal to 6 minus 2, which is equal to 4. Therefore, the criteria is LHS is equal to RHS. Similar way, when you apply the same phenomena for the slider crank mechanism, where 1 to 2 is a turning pair, 2 to 3 is a turning pair, 3 to 4 is a turning pair, and 1 to 4 is a sliding pair. There, even the sliding pair is also a lower pair. And if you apply the same criteria where there are 4 lower pairs which is equal to j and there are 4 links, and if you apply the same phenomena, 4 is equal to 3 by 2 into 4 minus 2, which is equal to 4 is equal to 4, and this is completely a kinematic chain, and we define this as the when you give a unique input, you are going to get a unique output. If you consider the link 2 is giving the input and link 4 will be an output criteria, and this is called as the kinematic chain with 1 degree of freedom. When we look at it, the unconstrained kinematic chain, when you look at it here in the same formulation, 1 to 2 is a turning pair, 2 to 3 is a turning pair, 3 to 4 is a turning pair, and 4 to 5 is turning pair, and 1 to 5 is a sliding pair. If you apply the same formula where number of links is equal to pairs is equal to 5, 3 by 2 into, and when you consider it is 5 minus 2, then this becomes 2.5, and this is going to be 7.5 minus 2, and this is 5. 5 is greater than 5.5. So, therefore, LHS is definitely less than RHS. Then LHS is less than RHS. In this criteria, when you look at it, definitely one input will not give the one output, or otherwise we require 2 inputs to get one unique output. The examples could be one input is giving 2 outputs is an automobile differential when only one input from the engine is given and 2 outputs are being taken through a different mechanism. And this is what the criteria of Goodbatch equation. Further, what is the degrees of freedom? It is the number of independent coordinates required to describe the position of a body. And when you look at it here, then there are the right hand thumb rule. If you look at it, there are a body is placed in the space and 3 mutually perpendicular directions x, y, z and rotation about that axis. Translation motion along any 3 mutual perpendicular axis x, y, z and rotation motion about these axes. Then the body is said to be having 6 degrees of freedom. Further, the degrees of freedom of a pair is defined as the number of independent relative motions, both translational and rotational, a pair can have. And it is defined as degrees of freedom is equal to 6 minus number of restraints. Restraints means where you are going to constrain that particular degree of freedom, either it can be translational or rotational. Degrees of freedom or mobility of a mechanism. It is the number of inputs, independent coordinates required to describe the configuration or position of all the links of a mechanism with respect to the fixed link at any given point. This is what we call it as the degree of freedom or mobility of a mechanism. Further, it is derived through a planar equation for the Grubler's equation or Grubler's criteria. The number of degrees of a freedom of a mechanism is given by where F is equal to 3 into n minus 1 minus 2j minus h, where F is degrees of freedom, n is the number of links in the mechanism, where j is the number of lower pairs and h is the higher number of pairs. With this is achieved through a link relative motion, and the explanation can have like this. If you are going to have 2 links in a planar mechanism where all the links will be moving in their parallel to the planes. And if there is a link that is there, and there is one more binary link that is there in a plane mechanism, say this is the P and this is going to be the Q. This is the P and this is going to be the Q. And Q. And if in a plane, this is y-axis and this is the x-axis. In a plane, in the x and y direction, how this equation has come, that is the objective of the present discussion. The binary link P can have 3 degrees of freedom. If you look at it, it can move freely in the x-axis. It can also move freely in the y-axis. It can also rotate about the x-axis. The remaining 3 degrees of freedom, rotation in the yz and translatory motion in the z-axis, is constrained in a planar mechanism. So the independently link P has got 3 degrees of freedom. Independent, the link Q has got 2 degrees of freedom. Further, if you join these P and Q, at this point where I have given the indication, that particular joint constrains P from moving in the x direction and Q from the moving in the y direction. But only one possibility is keep P constant, then Q can be rotated in either direction. That's the reason any link that is having in a plane mechanism can have 3 degrees of freedom. But a mechanism is defined in such a way that if a 4-bar mechanism, if you take a Q of it, 1, 2, 3, 4. One of the links is fixed. Therefore, if the mechanism is having n links, one link has to be fixed. The degrees of freedom for the mechanism is given as 3 into n minus 1. Further, if the mechanism is having number of lower pairs, then as we have derived in the link relative motion between P and Q, 2 degrees of freedom has been lost. Therefore, 2 into number of lower pairs. And for every higher pair, 1 degree of freedom is lost. Therefore, H indicates 1 into H. Therefore, this is called link relative motion, where this is the equation given by Grubler, and this equation we call it as the Grubler's criteria, and F is equal to 3 into n minus 1 minus 2j minus h is a standard equation for finding the degrees of freedom for any planar mechanism. So, next if we go for the examples based on earlier experience with the Goodbatch, if you look at it, F is equal to 3 into n minus 1 minus 2j minus h. Here n is equal to 4, j is equal to 4, and there is no higher pair. Therefore, F is equal to 3 into n minus 1 minus 2 into 4 is equal to 1. That is, one input to any one link will result in definite motion of all the links. Therefore, for the more clarity, I will say that 1 to 2 a turning pair, 2 to 3 a turning pair, 3 to 4 a turning pair, and 1 to 4 a turning pair, or turning or revolute pair, turning or revolute, turning or revolute. All these are lower pairs. Hence, a 4-bar mechanism is a kinematic chain with 1 degree of freedom. That indicates one link will give you the definitely one unique output. That is what we call it as the Grubler's criteria. And further examples, if you consider here, if there is a 5 link mechanism If number of links is 5, j is equal to 5, h is equal to 10. Here, if you consider the 12 minus 10, 2, that is 2 inputs to any two links are required to yield definition motion in all the links. That is what we call it as, to get unique output, two links should get the two unique inputs to get a one input which is regulated or coordinated. And if you look here again, f is equal to, for a mechanism containing 6 number where link 1 and link 3 are the ternary joints. Here n is equal to 6, j is equal to 7 and h is equal to 0. F is equal to 3 into 6 minus 1 minus 2 into 7, which is equal to 1. That is, one input to any one link will result in definite motion of all the links. This is another example. Here also we are having 6 and 2, 3, 4. That is also a ternary link where n is equal to 6, j is equal to 7. At the intersection of 2, 3 and 4, two lower pairs are to be considered. H is equal to 0. So please make a note of it. 2, 3, 4 is considered as the ternary link. And this is also where n is equal to 11, j is equal to 15, two lower pairs at the intersection of 3, 4, 6, 2, 4, 5 and 5, 7, 8, 8, 10, 11 and h is equal to 0, and therefore f is equal to 0. And it indicates the philosophy. What is the concept is, it is a redundant structure and there is no relative motion between the members. It is a structure. And if we consider the mobility of the following, when you consider the diagram A, f is equal to 3 into n minus 1 minus 2l into h, where l is equal to 5, h is equal to 0, and definitely it is a structure. There is no possibility of relative motion. Here you are going to have one higher pair in the B diagram. 3 into n minus 1 minus 2l minus h, that is also equal to f is equal to 1 with higher pair, and this is a cam and follower. And here also, when you consider the link is, the follower is welded to the lever. So therefore, there is no relative motion between those links of welded component, and it is also going to yield only 1 degree of higher degree of freedom. Hence, it is also going to give the 1 degree of freedom at the mechanism. And what is the advantage of Grubler's criteria? By understanding the degrees of freedom and mobility in a mechanism. And the figure shows a Watt chain in which the ternary links are directly connected. Thus, any of the binary links, if you refer to the links 2 and 6, can be replaced by a slider to obtain the slider crank mechanism. And the figure shows two variations of the slider are applied by replacing the binary link 6. The slider crank mechanism is known as a beam engine. And when you apply the Grubler's criteria containing a higher pair, as previously we have given, the number of degrees of freedom of a mechanism is given by f is equal to 3 into n minus 1 minus 2j minus h, where j is equal to 2 and h is equal to 1, and one input to any one link will result in definite motion of all the links. With this, we completely understand about the Grubler's criteria, and with this, thank you.
Like, share and subscribe. Hit the bell icon for more updates.